Hello and welcome back. In this segment, there really isn't anything conceptually new. We've broken the discussion of structs into different parts where in this segment we'll discuss the issue of pointers to structs. So we already know about pointers to primitive data types, and we've looked at using pointers to go through an array of primitive data types like an array of ints or doubles and so on. But the pointer to the struct, people tend to find it a little more difficult, but there's nothing new here. You have a variable, it has a data type, you can have the address of that variable, and you can carry around the pointer to that variable. We have the same issues with pass by reference and pass by value that we had before, just the added dimension of now, instead of using addresses of the primitive data types, we're using the addresses of the data types that we've created ourselves using struct. We're going to use approach 3, where we use a type def to define our structs, and that will be fairly consistent throughout the rest of the video segments. So let's have a look now at the issue of pointers to structs. So this is a continuation of the previous segment where we introduced structs and why you would use them, and the 3 ways of using structs, and approach 3 is the most useful, where you use type def to give the name for your new data type. So in approach 3 of the previous segment, we defined a data type called date using type def and then the struct and then give it a name. And we looked at how you could use that new data type to declare something of that type. So here's the picture that we have. When we declare birthday, we have an object that has a month, a day, and a year, the 3 component parts of that thing. Remembering from when we talked about pointers in previous segments, any data type has a corresponding pointer data type. So just by making this struct called date, we have now the ability to declare a date pointer. What is a date pointer? It is the address of a date. So I declared one called pBirthday, which is a pointer to a birthday, and here it is in the picture. The pBirthday gets the address of birthday. That means that the address of this thing, wherever it is in RAM, can be stored in this variable pBirthday, and that's what this is doing. So exactly the same syntax that we used to talk about primitives and pointers to primitives. The only difference here is that the name of the data type is something that we have made up ourselves. We've using a user-defined data type. And the issues for passing around structs is the same as passing around primitives. So you can pass them by reference or you can pass them by value. If you pass a struct by value, the function gets its own copy. This is the same as when you pass a primitive, like an int or a double, by value, the function gets its own copy. And the function manipulating its own copy does not change the data in the calling function. So we have the calling function and the called function. So we have a struct date. It's quite small. It only has 3 ints in it, but sometimes structs can be very large, lots of component parts, and structs can also contain other structs which contain other structs. So there could be a kilobyte of data or more in one object that's being passed to a function. So then the issue of, does the function really need its own copy? Because the size of the data that we're passing around, if it's large, we don't want to make copies of it. So maybe we would want to pass a struct by reference, even if it's not required that the function change the data. So up until now, when we're passing around primitives, we've said if you need the function to change the value, then you would pass by reference. And if you don't, you would pass by value. When you're passing structs, it often makes sense to pass by reference anyway, just because the function would have its own copy if you passed it by value, and that might start to get quite wasteful. So here's an example of passing a struct by reference. It's not any different than passing the address of an int or the address of a double. So let's back up a little bit and let's look at the definition of a function that we saw in the previous segment. First of all, this is a function that will print out a date, and what gets passed to it is a date. The same function could be written to take a pointer to a date, and we would be taking then just a small bit of data, one address, a pointer to a date, and this function, the second one here, wouldn't take up as much space in RAM, but it has the same objective. So now here we have something new. When you have a pointer to a date and you want to access its component parts, we have a new operator. It's not the dot operator. The dot operator works when you have a struct on the left. That's how you access the component parts of a struct. But when you access the component parts of a pointer to a struct, then we're going to use this new right arrow operator. And in this slide we talk more about that right arrow operator. First of all, going back to a function that accepts something by reference. So here's a function that accepts a pointer to an int, or the address of an int. And when we were using that variable inside of the function, we use the dereference operator. So we say what's pointed at by pvar gets 27. So the address was passed in, we go to that address and put 27. So look at this second piece of code that demonstrates a pass by reference for structs. So we pass in a pointer to a date, and we have to dereference that pointer. So this is awkward. We could say what's pointed at by pMyDate, and then go and get the day component out of that. So this syntax is very awkward. The dot operator has a higher precedence than the dereference operator, so we need to use parentheses to force the dereference operator to happen first, and then put the dot operator after the parentheses. So the moral of this is they added this operator so that all of this sequence of awkward syntax is not required. They do exactly the same thing, and it would be a good idea to type this code and see that it actually does work. It does put 31 into that variable, but this is the much simpler way of dereferencing the pointer to actually get at the component parts of the struct. Here's the picture. Keep it in mind. pBirthday, or pMyDate, is the address of this thing. So what's pointed at by this address is the whole thing, and then go and get the component parts. So there's the syntax for what I just said. Dereference the pointer to the struct, and then go and get the component part from the struct. A few more issues in this segment about working with structs. The size of operator. We looked at that very early in the semester, where you can ask for how many bytes there are in a data type. Well, now that we have our own user-defined data types, you can use the size of operator to find out how many bytes there are in your own user-defined type. So let's look at a new struct. Suppose we want to have a representation of an address. Well, what are the component parts of an address? Maybe address line 1, address line 2, and a zip code. And these are character arrays. So what would the size of this struct be? The size of address is 30 bytes, 60 bytes, 70 bytes. When you define a struct that has a string in it, and these are strings probably, or so null terminated character arrays, you don't want to just define this as a car pointer. So a car pointer is what you get accustomed to as using as the data type for a string. If someone declares one of these things and it has 3 car pointers in it, what would the size of address be? Well, a pointer is only 4 bytes of space. So that would be the size of address is only 12 bytes. When the size of address, you need to have enough room to hold the address lines and the zip code. So you don't want to be using car pointer here unless you're very, very careful with it. Here's another one. In this case, we're defining something called a customer. What are the component parts of a customer? Well, a customer has a name and an account number and an address. Well, where did this thing come from? That was our own user-defined type that we defined just up here. So keeping the customer data type neat, we didn't put address line 1, address line 2, and zip in here. We used our data type to make a nice representation of what an address is, and now we can use that in our definition of the customer struct or the customer data type. These can become arbitrarily complex. You can use your own data types however you would use the primitive data types, including as component parts of newly defined data types. Okay, we haven't looked at the keyword const up until now, so let's look at that. Keyword const means that something is being kept from changing. So in this first example, const double tax rate gets 0.07. What we're doing is we're defining this variable to not vary. As long as this program runs, we don't want this variable to ever change from 0.07. So you cannot write a line of code that says tax rate gets 10.0, for example. This variable is defined to be protected at its initialized value. You can also use the const keyword to prevent array elements from being changed. So here's an example of using the const keyword to protect the data in this array. Okay, why is that useful? It's a defensive programming mechanism. If you want to prevent yourself or others from changing a piece of data, then you would use the const keyword. It can also be used to modify a parameter. So remember when we were passing a date object by reference, our objective of passing it by reference was so that it wouldn't take up so much space. The function doesn't need its own copy just to print it out. But it also doesn't need to change it. And we don't want to risk that the data would be changed. So we have those objectives. We want to not waste space, so we'll pass by reference. But we also don't want to risk that the function would change our data, perhaps accidentally or intentionally. So the parameter is going to be modified by the keyword const, and that will prevent someone from changing the struct that we've passed into the function by reference. So this function, whose job is to print out a date, has no business changing the day component to 158. And to prevent that from happening, we use the const keyword. Okay, so we've been looking in this segment at the issue of pointers to structs and passing structs around. You might find this very easy because all of the concepts are the same as they were in the previous segments. So here's just a brief summary of what we looked at. Passing a struct to a function is a pass by value unless you pass a pointer to a struct, and that would be a pass by reference. Keep in mind that anything that you pass to a function by value, there's a copy made of it. So when you pass a struct around, even if you don't need the function to change anything about the struct, you might want to pass it by reference. So especially if these structs become very large and you don't need another copy of it in the function that you're passing it to, then you might want to pass the struct but to the function by reference. We have a new operator in this segment, the right arrow operator, and it's used as a shortcut of dereferencing a pointer to a struct. So you can get at the component parts of the struct without having to dereference and then use the dot operator. So this right arrow operator is used when what's on the left is a pointer to a struct or the address of a struct. You can also, when you pass a struct by reference, you can use the const keyword to keep the function from changing the struct. And that's a defensive programming technique, so the issue there is someone would accidentally inside of a function change the data, and you would be tempted to then say, well, I'll pass it by value so that they can't change my copy of the data instead of passing it by reference. And the way around that is to pass it by reference, but use the const keyword on the parameters so that the code inside of the function cannot change the data that you're using in the calling function. Structs can be composed of primitive variables, or they can be composed of any other data types that you have. So our user-defined type might be composed of other user-defined types. So a customer struct might have as one of its parts, its component parts, a phone number struct. And a phone number struct might be composed of some other struct. So you can kind of make layers of these things as your problem gets more complicated. When it gets too complicated for anyone to work with, then you probably should stop doing that. But you have that ability in the language to put any kind of a data type inside of your struct that you want to, including other structs. The size of operator is very useful when working with structs, and it will be more useful in the upcoming segments where we dynamically allocate memory from RAM to hold our data. So the size of operator can be used to find out how many bytes there are in a data type or in a variable, and we want to make sure that you keep that one in mind. It'll be very useful as we go along. Okay, I hope you're comfortable with working with pointers to structs, and let's move on to writing some code that gives you some more examples of exercising this concept.